Okay, in this short video, I'm going to introduce the idea of inductors and capacitors. Okay, so capacitors is something that you would have been familiar with from your A-level course, and we're just going to look at the idea of an inductor, and an inductor is essentially just a coil of wire. So here I have a circuit and I have a coil. Okay, and a capacitor. Here I would have a cell and it has a capacitor, like so. Okay, now what we can say is at DC, that is direct constant current, ideal inductor has a resistance equal to 0 ohms, it's just a wire, and an ideal capacitor has a resistance that is infinite because it's an open circuit. So we're going to look at this idea of an inductor essentially like a mirror component for a capacitor. So we're going to see how the relationship between current and potential difference for an inductor and the role of the inductor is similar to that of the capacitor, but in some ways could be said to similar but opposite in other ways to the role of the capacitor. Okay, so if we look at the circuit which has a coil, we know from GCSE that there is a magnetic field around a current carrying coil. Okay, and if we wanted to say how much or how large is that magnetic field, we can say that the magnetic field density is equal to the permeability times the number of turns over the length, the turn density, multiplied by the current. Now you'll notice that all of a sudden, whereas certainly in GCSE you will have been used to circuits drawn with a capital I shown for current. The standard notation typically used, particularly in textbooks, is that we use a small letter I and a small letter V whenever we're talking about currents and potential differences that are changing. So we'd like to see what the relationship is between the potential difference across a coil and the current flowing through it. Okay, so this is saying this is the relationship for the magnetic field around a current carrying coil. Okay, now when the circuit is switched on, the current ramps up to a maximum. Okay, and in that case, that the relationship between the potential difference across the coil and the current is going to be given by this relationship. So the potential difference across the coil is equal to the current times the resistance of the coil, probably quite small, which gives us that the current is equal to potential difference over resistance. Okay, this is when the current has reached its maximum DC value. The question is what's happening as the current is increasing. So obviously when the circuit is off, the switch is open, then there is no current flowing. So what happens in between switching the circuit on and the current reaches its maximum? What happens as the current is changing? So we know that, and by the way, in this case then my magnetic field strength is given by times I, where I is the maximum current, the final DC current in the circuit. Okay, but as the current is ramping up, then the magnetic field Now the magnetic flux density is equal to, at a particular moment, here I've used little I, saying that the current is changing. And I can say that the magnetic flux, which is equal to B times A, that gives me that the magnetic flux therefore is equal to the permeability of free space N over L I times A. And I can just rearrange that just to put it here. I've got the constant terms times the current at that particular point in time. Okay, now how does that relate to the potential difference across the coil? Well, we know from Faraday's law that the EMF induced in a wire by a change in magnetic field is given by, minus from Lenz's law, n times the rate of change of flux. What does this mean? Okay, what do I mean by this? What I mean by this is that current flowing through the wire generates a magnetic field. The generation of that magnetic field in turn induces an EMF in the wire while the magnetic field is changing. Okay, so this is EMF induced across the inductor. So current flows through the inductor is generating the magnetic field, and that increasing magnetic field causes an EMF to be induced. This EMF is known as the back EMF, and from Lenz's law it is in a direction to resist the change that's causing it to happen, so to resist the current, to oppose the current that's causing the magnetic field to be generated. And because it is going back into that same coil, this is known as self-induction. So this is an inductor, and this process is known as self-inductance. Okay, so let's see what we can find for the rate of change of the flux in this case. So from the previous page, we had this equation for the flux. So that was equation 1. We make this one equation 2. And Faraday's law, equation 3. So we had equation 2, which told us the expression for the magnetic flux. And we had, that was 2, and we had Faraday's law telling us the EMF induced rate of change of flux. So let's substitute in here. So the EMF is equal to minus n, rate of change of flux, but flux is given by this term. These are constant, so I can take them out, and that gives me minus permeability times the area times the number of turns squared over the length, di over dt. So this is our relationship between the back EMF induced in the inductor and the rate of change of the current. And I can write this now as the potential difference, or rather the potential difference across the inductor is given by L times di over dt, where L is equal to minus mu naught an squared over L. Okay, this term L is known as the inductance, and it's measured in units of Henry's H. Okay, and we make this one, this is going to be equation 4. Okay, that's going to be equation 4. And what I'd like to just do here is just introduce the equation for capacitance, so just so we can make the comparison. So this was the equation relating potential difference across the coil to the current passing through it, and we can compare that to the capacitor equation, which is current is equal to the capacitance times the rate of change of potential difference. So we saw that Under DC conditions, the inductor ideally has a resistance of 0. The capacitance has an infinite resistance open circuit. In terms of the what we call the transient characteristics, as the current is changing, when we've just switched on the circuit, we have a relationship between the voltage and the rate of change of current. In the capacitance, when we switch on the circuit and it's charging up, the current is equal to capacitance times the rate of change of voltage. And for this expression, it's relatively trivial to get from that to the expression that you would have had from in A-level physics. Capacitance equal to charge over potential difference. Okay, so let's continue on looking at comparing inductance and capacitance. So one thing that we look at in capacitance is the time constant. We look at the transient characteristic of the capacitor, that is, when it charges up and discharges, the relationship between current and voltage and time. So we're going to do the same thing here. Here I've got an inductor and some sort of resistance. And what's going to happen in a similar way to capacitors, we will have the current is going to ramp up over time, which could be measured in seconds. I'm just going to write it down as time constants. So that's going to be 1, 2, 3, 4, 5. Okay, and it's going to ramp up until we get to V over R, and then it will stay constant. Okay, so the relationship is given by similar expression to capacitance, which is the current is equal to I times 0 times 1 minus e to the minus t over tau. And this is known as the time constant. And in the case of the inductor, it's given by the inductance over the resistance. And we know that in the capacitor, the same parameter, the time constant, is given by resistance times capacitance. In the case of the inductor, it's the inductance divided by the resistance. Okay, so let's explore the similarities further and look at energy. So as this current ramps up, the inductor the inductor has a back EMF induced in the inductor as the current ramps up. That's working to oppose the changing currents that's generating the magnetic field. So work has been done, which means that energy is stored in the inductor in the same way as energy is stored in the capacitor. And we can determine how much energy is stored by using power is equal to V times I, and that gives me, substituting for the V term, that gives me power is equal to I times L di over dt. Now to get the energy, I need to integrate the power over the period of time as taken to get up to the maximum current. And I can substitute for power, which gives me, this is going to be the integral of Li di from between 0 and I, which gives me a half Li squared, where I is the final DC current. So the energy stored in an inductor is equal to a half Li squared, and the energy stored in a capacitor is a half CV squared. So once again, we see the corresponding equations between inductance and capacitance. Okay, so we have the energy stored of these equations. We had, so if we summarized everything we've got, we have inductance, or the inductor, and the capacitor. If we start at DC, this is short circuit, and this is open circuit. the relationship between voltage and current is equal to L, rate of change of current, whereas here we've got the current is equal to the capacitance times the rate of change of potential difference. We had that the time constant for the inductor is L over R in a circuit with a resistance, whereas in capacitor it's R times C. And then finally we had the energy stored in an inductor is Li squared, whereas the energy stored in a capacitor is CV squared. So essentially the capacitor acts to oppose the change in potential difference. The inductor acts to oppose the change in current. So the next step to explore the operation of these components, circuit components, further is to start looking at the concept of impedance.